Hi, welcome to our last lecture on Big Data and Introduction to Statistical Learning. And in this lecture I'm going to discuss some classical methods of statistical learning literature. And first I will discuss a method that selects the best subset of variables. It is it's not very difficult, but it's quite intuitive, and it's good for introduction. After those methods, we will move on to shrinkage methods. And in particular, we will discuss two types of shrinkage methods: ridge regression and lasso. And then after that, I will spend some time on discussing tree-based models, and in particular I will discuss the most classical CART algorithm, which CART stands for Classification and Regression Tree, and then I will discuss a bit about extension of CART algorithm to random forest. So that's the roadmap for the rest of this course. So let's start. First, let's start with discussing selection of the best subset of variables, and this is the method which comes from the classical econometrics. Some of you may know this class of methods. And let's start with this. So suppose that we have some phenomenon, our outcome variable, that we would like to predict, and we would like to have a model which provides the best prediction, and we don't know which other variables are the best predictors. Combination of those variables together is the best predictor of our outcome variable. And in this exercise, we will use the data set from the library, which is complementary to our textbook. And this data set is called headers. Okay, I needed to pause here because there was a helicopter. Hopefully it wasn't a helicopter with helicopter drop of money, in the spirit of Milton Friedman. I'm joking. So we will use dataset headers. And this dataset is a description here. This is data from Major League Baseball, American League, for season 1986-1987, and in this exercise we want to build a model which we have here. We have several variables. The variable of our interest that we would like to model is salary. It's over here, and we have 19 other variables that we can use for making prediction about salary. If you watched Moneyball movie, we would play a similar play to the main character, but unfortunately not played by Brad Pitt, but the other guy, Jonah Hill, I guess. So we will use statistics to make the best, to build the best model that predicts salary. In Moneyball, it was performance of the player. Here we will build a model that predicts salary in the best way possible. First, check how many variables, how many observations of for variable salary is missing. Yeah. Okay, we have 59 observation missing. Yeah, I don't know whether we talked this before. I think that we may have talked about this, yeah, but if not, in R and also in other data-oriented languages, NA stands for missing observation. Yeah, and in our model, if we want to build the model of salary, yeah, if we don't have information about salary of some players, it's better just to eliminate all missing observations. We can do it by using command naomit. So before applying this function, we have 59 observations for this for headers missing. If we apply naomit and then assign this value to headers, we will get 0. Yep. To find the best model predicting salary, we will use a library called libs, and in this library there is command reg subsets, which does the following thing, yeah, that for each number of variable, it compares all combination of different variables. Okay, maybe let's run this function first, and then I will explain what it does. Data headers. Here we provided that we want to find the best subset of variables for explaining salary, and tilde and dot means that we use all other variables from dataset headers. And let's assign the output, the outcome of this command, to regfit full. Yeah. So now, if I type summary regfit full, I will get the following thing. That for this command proceeds in the following way, that for each number of variable, here we have number of variables from 1 to 8, and for each number of variable, R checks what combination of variables are the best for this number. So yeah, it sounds complicated, but let's describe this using this example. So here we have 1, and then R compares models of salary with only one variable, one of those 19 variables, and chooses the one which is the best. So in this case, this is CRBI, and this model, according to R, is the best in the class of models with only one variable. Okay, and then for two variables, then R computes all combinations of runs many models with two variables, all combinations of pairs, and then reports this model, which is the lowest mean square error. So here, this model uses, with two variables, uses hits, yeah, and CRBI, okay, and it performs, yeah, that for each combination of that for 3 it does exactly the same thing, and yep. Okay, yeah, so here we have So overall, this command computes a lot of different models. To be precise, so if here we used only from 1 to 8, if we want to explore all combinations up to 19, we have to provide nvmax function, which provides the highest number of variables included. Yeah. Okay. Rec fit full summary. And here we have the best models. Yeah. Depending on the number of variables, we have the best. The selection, the star, accounts for including this particular variable for a model with this number of variables. I admit that this way of illustration of results is not the nicest, yeah, and alternatively we can plot the outcome of using function rec subsets, and here we can provide different scales. Among others, there is R-square, some information criteria, but let's use R-square, which is R2. Yeah. And here we have the result, the illustration, a similar illustration to this, but a bit nicer. Yeah. So here we see that the best model with one variable is with variable CRBI. With two variables we have CRBI and heats, and so on. Yeah, and also those models are ranked here on y-axis. We have R-square, and there are two remarks that I would like you to remember from this figure. Here we have ordering. First remark is that this ordering is that variable with the model with more variables always has higher R-square. It is by construction. Yeah, and the model, the best model, is with all variables. The worst model is only with one variable. Yeah, and there is no single case where there would be a model with fewer variables that would have higher R-squared. Yeah, so that's the first observation. The second observation is that some variables that are included for fewer number of variables, at some point they are dropped and they are replaced by other variables, and it is visible for variable CRBI. Yeah, so for this, at some point, it's better to use other variables. Yeah, and this shows that that to truly explore the whole space of potential models, we have to test many different specifications. Yeah, and this is the way how we build here. This how we compare those models. It is called exhaustive search. Yeah, that we conducted this search of all potential combination of variables. Yeah, and then we chose the best models in the class of number of variables. Yeah, and and this is it. Yeah. Yeah, the only thing is that here we compared all models, but we had only 19 potential variables, and from combination, we can compute how many models for this exhaustive search were computed. This is 2 to the power of 19. Yeah, and in comparing all those models, we ran almost over half million different specifications. And here we illustrated only the best 19 specifications. Yeah, so this model, yeah, is the best, the best that we discuss in this part, but computationally it's quite costly. Yeah, so now we will move to some substitutes which are not perfect, but can be used for cases with much more many variables, because here we had only 19 variables, and in real world problems the number of potential variables is very often way larger. Yeah, and then we cannot use this exhaustive search. Yeah, and we have to do something which does similar job, but it's faster. Yeah, so that's the plan for the next cut. Now we will consider two alternatives for so-called exhaustive search, where we compare all possible combinations of variables, and those alternatives are forward selection and backward selection. Yeah. So if we want to perform, let's first use forward selection. It's enough that we provide as a method forward. Yeah, and let's change this name here. Okay, and to plot the result of this of forward selection, let's use main, also title, selection. Okay, so that's the result of forward selection of variables, and it works in the following way. Yeah, that first the model with the best model with one variable is chosen. Here in this, let's zoom this. So here CRBI is chosen. Then in the next iteration, so for sure we keep this variable in all our future iterations, and now we're wondering only what's the next best pair for this variable. Yeah, so instead of comparing all combinations of all potential pairs, we know that for sure we will keep CRBI here. Okay, so instead of computing much more models, here we check what's the best variable together with CRBI. If we have the best pair, then in the step with 3 variables, we compare all those. What is the third best variable in addition to those 2 that we already chosen? Yeah, so it's a bit different, and yeah, so it's a bit different approach. And yeah, here notice that this is intercept. Yeah, so it's not considered as a variable. Yeah, and overall, yeah, the implication of this approach is that if we choose one variable at the earliest stage, it will be kept forever for sure. Yeah, and if we notice, if we compare this with exhaustive search, just like here, it wasn't the case. Yeah, so here for the model with I don't know how many variables are here. Yeah, but all potential combinations were chosen, and it turned out that CRBI is not important anymore. Yeah, so this is forward selection. Backward selection method works in the opposite direction. Yeah, and if we take this, we provide here backward. philosophy of this is slightly different, because here we start with the full model and then we're considering what dropping what variable is the least costly in terms of reducing our residual sum of squares. So here before we were starting with intercept, and we were adding one additional variable. Here we start with the model with all variables, and we're wondering what variable should be dropped. And this method is not; those two methods are not equivalent to each other. And the easiest way to see is that those plots are slightly different. CRB, according to backward selection, this variable CRBI was dropped quite in the middle. While for forward selection, it was chosen as in the very beginning. So at the end we can end up in different models. But again, computing model with forward and backward selection, it is much faster because we don't explore such a wide space of potential combinations. What I can say more is that the advantage of overall, if we can use, we should use exhaustive search. If we cannot use exhaustive search, that's my recommendation, is the best. If we can, we should use both forward selection and backward selection, and then see which model is better chosen by those two different approaches. But we will talk about this in the next part of this lecture. And the very last comment that I want to make is that the advantage of forward selection is that we can consider from time to time we may have more variables than observations. And if we have more variables than observations, then forward selection is the only way that we can proceed. Because in backward, according to backward selection, we cannot. If we have more variables than observations, then we cannot estimate the model. So that's one comment. And and I think that this is it for this part of the lecture. And in the next part, I will try to talk a bit about how to marry those subset selection methods that I discussed today with cross-validation approach. So it will be So that's the plan for the next part. Okay, so see ya.